Good morning students. Today we are going to study different types of problems which is associated with the Dalton's law of partial pressure, vacuum efficiency and condenser efficiency. The first of all, we will going to revise the laws of this involved in the condenser, the Dalton's law, partial law of pressure. This is the Dalton law of partial pressure. In this case, according to this pressure, where the statement is that the total pressure exerted by non-reactive mixtures of gases or mixtures of gas and vapor is equal to the sum of partial pressure of individual constituents of mixture at the same temperature. That means in this case what happens, there are the you are considering the steam and air at temperature T having a total pressure, and the second is the steam alone at temperature T at a steam pressure, and the another one is the air alone at temperature T at the PA. This is the Dalton's law of partial pressure. What is happening in this case? The partial pressure of each constituent in the mixture, pressure exerted by the constituent taken separately in the same volume of the vessel. That means the pressure exerted by these combine steam and air, and the pressure exerted by the steam, the pressure exerted by the air. That this diagram indicate that the total pressure in the condenser is nothing but the addition of sum of the partial pressure of air and partial pressure of steam. So we can conclude that means according to the law, what it means, according to the law, total pressure equal to the pressure, steam pressure plus air pressure. And this one we can from this law we can conclude that the total pressure in the condenser. Vacuum pressure reads the total pressure in the condenser, that is PT, and the steam pressure PS can be known from steam table corresponding to the pressure condenser pressure. That is the condenser pressure as total pressure and PS are known, then we will determine partial pressure. That means from Dalton pressure we can find out the total pressure. This is the importance of that law. We have to find out the total pressure inside the condenser. Then we discuss about the another parameter, the vacuum efficiency. The value of the vacuum efficiency, for this all these efficiencies were important for to solve the numericals. Therefore, vacuum efficiency is nothing but the degree of reflection, degree of perfection of maintaining a desired vacuum in the condenser. What it means? The degree of perfection of maintaining desired vacuum. That is how much amount of vacuum is developed, how much vacuum is generated in the condenser. That what is happening in this case? The ideal vacuum means nothing but the vacuum due to the steam alone. That is the vacuum. Ideal pressure vacuum means the steam alone when air is absent. When the steam is present, what is the vacuum? That is the ideal vacuum. Under such a condition, the total pressure in condenser will reach the pressure of steam corresponding to the saturation pressure of the steam. That means under such a condition, total condition, the we have to determine the different pressures, the steam pressure, that is the total pressure, and barometric pressure. The PS means saturation pressure of steam in bar corresponding to the temperature of water entering the condenser. That means the steam having a pressure and entering into the water into the condenser. The steam having some pressure, enter into the condenser, that is the PS. Then total pressure, PT means total pressure of air and steam. That is the addition of the total pressure. That means air pressure plus steam pressure. Then discuss about the another pressure is the barometric pressure. That is also known as the atmospheric pressure. That is how to determine the ideal vacuum is determined that with the PB minus PS, that is the atmospheric pressure minus saturation pressure, will give the ideal vacuum. Then go to the actual vacuum. Actual vacuum is nothing but the again the barometric pressure minus total pressure. That is the discussion of the whenever you find out the ideal vacuum or actual vacuum, you have to subtract. So you have to subtract the steam pressure and subtract the total pressure. Finally, we can determine actual vacuum equal to PB equal to PB minus PA plus PS. Then we'll discuss about the definition of this one. What is the definition of this one? The definition is that nothing but this is a ratio of actual vacuum recorded by the vacuum gauge to the ideal vacuum. And therefore we can write down the equation for that one. N vacuum equal to PB minus in bracket PA plus PS bracket complete upon PB minus PS. We get the final equation PB minus PT divided by PB minus PS. This is the final equation for the N vacuum condenser vacuum. That means in the condenser there the air leakages problem are there, air source are there. Then we discuss about the if there is no leakage in the condenser, suppose there is no leakage in the condenser, that means a pressure of air equal to 0, then vacuum efficiency will be considered as 100%. This is the main thing. That means air leakage not present in the condenser, that means the 100% efficiency vacuum efficiency. Then we discuss about the vacuum efficiency depends upon the effectiveness of air cooling and the rate at which the air is removed by the air pump. That means the vacuum efficiency only closely related to the air parameter, and the vacuum efficiency equal to 98 to 98%, generally 98 to 98%, 98 to 99%. Then discuss about the last efficiency, because all efficiency are only considered for the numerical purpose, therefore discussing here, because all are this topic already covered the theoretical portion. We already completed the unit, but we have to take the revision of the topic. Therefore we discuss about the condenser efficiency. Condenser efficiency, that means nothing but the rate of actual rise in the temperature of cooling water to the maximum possible rise is known as the condenser efficiency. In condenser efficiency, what happens in this case? The steam to give the its latent heat to circulating water. What is happening? The steam has energy is ejected to the cooling water, so that the temperature of condensate becomes equal to saturation temperature and correspond to the condenser pressure. Again, it means there should be no undercooling of the condensate. Maximum temperature to which the cooling water can be raised is the condenser temperature. The condensation efficiency, the thing, but again I will discuss about the actual rise in temperature of cooling water. That is the temperature of cooling water increases to the maximum possible. That this is a and we can this N condenser is represented by the equation T2 minus T1 divided by Ts minus T1. That means T2 means outlet temperature of cooling water, T1 means inlet temperature of cooling water, and Ts means saturation temperature correspond to the condenser temperature. And these are the efficiencies we have discussed here and last discussed here. Then go to the main topic, the numerical based on the condenser. Numerical based on the condenser. We will take the first numerical. The following readings are recorded during a test on a steam condenser vacuum in a condenser equal to 71.5 centimeter of Hg. Then barometer reading equal to 76.5 centimeter of Hg. Then mean temperature of condenser equal to 33 degrees Celsius. Hot well temperature equal to 29 degrees Celsius. Inlet temperature of cooling water 9 degrees Celsius. Outlet temperature of cooling water equal to 26.5 degrees Celsius. Calculate first one, corrected vacuum to standard parameter. Second, vacuum efficiency. Third, undercooling of condensate. And fourth and last, condenser efficiency. First of all, we have to identify the numerical from this topic. First of all, this numerical based on the steam condenser. In the numerical, we have given this vacuum condenser. That the vacuum is developed in the condenser 71.5 cm of Ag. And in the same numerical, the barometer reading is given 76.5 centimeter of Ag. Temperature of condenser is given, hot well temperature is given, inlet temperature of water is given, and outlet temperature of water is given. Then you have to determine the corrected vacuum to standard parameter, then vacuum efficiency, and you have to find the condensate undercooling and the condensate efficiency. The first of all, you have to find out the N vacuum. That you have to N vacuum, that means vacuum efficiency. Vacuum efficiency requires the ideal vacuum and requires the actual vacuum. Then you have to first of all you have to find out the ideal vacuum, and then you have to go to the corrected vacuum, that is 76 minus HB minus HG. The HG means barometer minus gauge pressure. The 76 minus in bracket 76.5 minus 71.5 bracket complete 71 centimeter of Ag. We are getting the corrected value 71 centimeter of Ag. And then from this 71.7 of Ag, then go to the absolute temperature given in the numerical 33 degrees Celsius. And from 33 degrees Celsius condenser degree temperature, you have to find out the pressure. You first of all you have to open the steam table. From the steam table, you have to go to the steam table. You have to find out the value of temperature 33 degrees Celsius, and from 33 degrees Celsius, we are getting the 0.05029 bar pressure. And this pressure I have converted into the mm of Hg, because all numericals are converted in the form of mm of Hg. Then your conversion factor is 1 by 0.013322, and then you have to convert this bar into mm of Hg. Then 0.05029 divided by 0.013332 equal to 3.772 mm of Hg. So we are getting the pressure, absolute pressure of steam. Then you have to find out the n vacuum, that means the vacuum efficiency. You have to put the formula, and then you have to put the value 71.5 divided by 76.5 minus 3.772 will get the efficiency, vacuum efficiency 0.9831 multiplied by 100 will get the 98.31%. You are getting the vacuum efficiency 98.31. Now we have already discussed about the efficiency is ranging between the 90 to 99%. Then second parameter you have to discuss undercooling of condensate. What is mean by undercooling? That means undercooling nothing but the condenser temperature minus hot well temperature. That is the temperature developed in the condenser minus hot well temperature. Then we'll get 33 minus 29 will get 4 degrees Celsius. You are getting undercooling of condensate 4 degrees Celsius. Then go to the find the another parameter, condenser efficiency. We want condenser efficiency, that means we want the temperature of Ts. We have to find out Ts temperature, because T2 is already given, T1 is already given, but Ts temperature is not given. Then you have to find out Ts temperature. Then Ts temperature, the first of all, condenser absolute condenser pressure equal to barometric reading minus vacuum reading. This is the formula for the condenser pressure, absolute condenser pressure. Put the value 76 minus 71.5 equal to 4.5 centimeter of Ag. And again this centimeter of Ag coming into the bar, multiply by 0.013322 will get the into the bar. Then we have to multiply 4.5 into 0.01 equal to 0.05 bar. You are getting the absolute condenser pressure. And this pressure, from this pressure you have to consider this pressure, and you have to go to again steam table. From the steam table you have to locate this value, and you will get the temperature of saturation temperature. You will get the 35.85 degrees Celsius temperature from the steam table. We are getting the value from the this pressure line, pressure value. Then therefore maximum temperature to which cooling water can be raised 35.85 degrees Celsius. Okay, the last one, that means, and then put the formula for n condenser equal to T2 minus T1 divided by Ts minus T1 equal to 26.5 minus 9, 35.85 minus 9 will get the 0.6518, and then whatever by 100 will get 65.18. Finally, we get the efficiency of condenser 65.18. That means this numerical belongs to the condenser, and we are going to find out the vacuum efficiency, undercooling of the condensate, and find the condensate efficiency. This is the end of the first numerical. Then go to the another numerical. In the condenser vacuum. In a condenser vacuum, gauge reading. In condenser vacuum, gauge reading. Gauge reads 71.5 centimeter of Hg, while barometer reads 75.5 centimeter of Hg. The temperature of condenser is 25 degrees Celsius. Determine first one, pressure of steam and air. Second, mass of air per kg of steam. Third one, corrected vacuum to standard barometer, and last one, vacuum efficiency. Then this numerical again belong to the condenser section. Then first of all you have to read once again, you have to find out what is the input data is given, and you have to find out the output. In condenser, the vacuum gauge is there, barometer read is there, and temperature of condenser is given. The temperature condenser temperature is given, and you have to determine the pressure of steam air, pressure of the air. That means you have to consider Dalton's law of pressure, because you are given in the numerical. You have to find out the pressure of steam and pressure of air. So these two pressure coming from the total pressure. Therefore, you have to apply the Dalton's law of pressure, partial pressure. Then mass of air per kg of steam. You have to again find out the mass of air, how much amount of mass of air per kg of steam. Then you have to find the vacuum efficiency. The first of all, you have to find out first one, total absolute pressure PT in the condenser. Again the Dalton's law of pressure, HB minus HV equal to 75.5 minus 71.5 equal to 4 centimeter of Hg. Again this centimeter of Hg converted to the bar, multiplied by this factor, conversion factor. 4 into 0.01 2 equal to 0.05 2 bar. And from this pressure we have to find out the temperature of that. Then we have to go find out another parameter, partial pressure of steam at the temperature at the condensate temperature 25 degrees Celsius. Again 25 degrees Celsius, go to the steam table and we are getting the values of pressure of steam. PS equal to 0.03166 bar from steam table. Then partial pressure of air, then you have to find out, you already find out the value of PT, value of PS, and you are getting pressure of air. The pressure of air is getting from Dalton's law of partial pressure. Then write down the equation P equal to PT minus PS, you will get the value of this one. 0.05332 minus 0.03166 will get 0.02166 bar. So we are getting the partial pressure of air. Then at the same time we have to find out the specific volume of steam, 43.402 meter cube per kg, and this volume can be getted from this bar, from the ideal pressure. And then air will be occupied the same volume. Then apply the perfect gas equation PV equal to MRT, and apply the equation PA VA into MARTA. Put the value and we'll get the value of mass of air, 1.094 kg per kg of steam. That in this case, in this numerical, you have to apply PV equal to MRT, perfect gas equation. And from next parameter, you have to find corrected vacuum. Corrected vacuum is 76 minus HB minus Hg. Again, you have to put the values. We will get a 72 centimeter of Hg. You are getting corrected vacuum. And then find out the last parameter, vacuum efficiency. How to find vacuum efficiency? Vacuum efficiency find out nothing but the actual vacuum recorded by gauge divided by the ideal vacuum. Then again, from the steam table, from the condenser temperature, you are getting the value 0.0316 bar. You have to again convert into the mm of Hg divided by 0.013332. We'll get the 2.375. We are getting this one, absolute pressure of steam. Then put the values. N vacuum equal to 71.5 divided by 75.5 minus 2.37 will get 0.9777, and multiplied by 100 will get the value 97.77%. That is, again we are getting the N vacuum efficiency 97.7. In this numerical we have determined how to find out the pressure of air, pressure of steam. That is, you have to apply the Dalton's law of pressure. Again you have to find out the vacuum efficiency. This is the end of the second numerical. Then go to the another numerical, the third one numerical. The third one again based on the condenser. A condenser deals with 900 kg of steam per hour with a dryness fraction of 0.9. The temperature of condenser is 40 degrees Celsius. The air associated with the steam in the condenser is 200 kg per hour. Determine the vacuum reading while barometer reads 75.5 centimeter of Hg. Correct this vacuum to a standard barometer reading of 76 centimeter of Hg. This numerical again belong to the condenser, and in this case the given data is there. The steam mass of steam is given per kg per hour. Mass of steam mass of steam per hour is given, having a dryness fraction 0.9. That is again the steam is a wet disaturated wet steam 0.9. Temperature of condenser is given, mass of steam is given, having dryness fraction is given, temperature of condenser is given. Again, the air associated with the steam, that is the air involved in the steam, is also given 200 kg per hour. Their air content is also given. To determine the vacuum reading, while barometer reads is given, and you have to find out this that the main is the vacuum reading. Have to find out in this case corrected vacuum. Again, you have to find out the corrected vacuum. Again, from this equation, from this numerical, first of all you go to the steam table. From steam table, the partial pressure of steam is given 40 degrees Celsius. From this temperature, we have to find out the pressure, steam pressure. From you go to the again temperature line, and from temperature line you are getting the pressure PS from the steam table. PS equal to 0.07375 bar. Then volume of 1 kg of steam at 40 degrees Celsius. Again you are getting the values from steam table. Vs equal to 19.55 meter cube. Then you have to find the total volume of steam. That means you have to multiply the mass of steam. Therefore, total volume of steam equal to mass into x into Vs equal to 900 into 0.9 into 19.55 will get the final value 15835.5 meter cube. Is the total volume of steam is getting. Then air will also occupy the same volume. Again in this equation the air occupies the same volume. Therefore again you have to apply the perfect gas equation. PV equal to MRT. PVMRT suffix A. Then put the values in this equation. We are getting the value of pressure of air. Pressure of air nothing but 1134.55 Newton per meter square. Then you have to again convert into the bar. That means you have to multiply by 10 to the power minus 5. So we'll get 0.011345 bar. You are getting the pressure of air. Then find out the condenser pressure. How to find out the condenser pressure? Again you have to condenser pressure nothing but the pressure 0. Pressure of steam minus pressure of steam plus the pressure of air. Addition of this total pressure means again you have to apply Dalton's law partial pressure formula. PT equal to PA plus PS. You put the value 0.07375 plus 0.011345. You will get the 0.085095 bar. You are getting the total condenser pressure. And then this pressure again converted into the centimeter of Hg multiplied by divided by this one 0.013322 will get 6.38 centimeter of Hg. Then multiply from this condenser pressure is also given, and you have to find out the vacuum reading, that is 75.5 minus 6.38 will get 69.12 centimeter of Hg. You are getting the value vacuum reading 69.12 centimeter of Hg. Then next find out the corrected vacuum, that is again 76 minus in bracket 75.5 minus 69.12 equal to 69.62 centimeter of Hg. That means you have to getting the values, the vacuum reading values were given and corrected vacuum. That means in this numerical we have given the mass of steam is given, mass of air is given, and in this case mass of steam, in this equation you have to find out the volume of air, volume of steam have to find out at 40 degrees Celsius. Therefore today's session is belong to nothing but the numerical based on the condenser. That means in this numerical you have to maintain, you have to understand the value of condenser vacuum, condenser efficiency, and this is the end of the today's session. Then we'll take one more numerical on the condenser. The following data are recorded during the test on a steam condenser. Vacuum in condenser 71 centimeter of Hg, barometer reading 76.5 centimeter of Hg, mean temperature of condenser 35 degrees Celsius, hot well temperature 20 degrees Celsius, inlet temperature of cooling water 8.5 degrees Celsius, outlet temperature of cooling water equal to 25.6 centimeter, condensate collected 1900 kg per hour, and cooling water quantity 59,500 kg per hour. Calculate corrected vacuum to standard barometer, vacuum efficiency, undercooling of condensate, condenser efficiency, quantity of steam entering the condenser, and mass of air present per meter cube of condenser volume and per kg of uncondensed steam. So in this numerical, again the numerical belongs to the steam condenser. In this numerical, what is given in the data? Vacuum condenser is given, barometer reading is given, mean temperature of condenser temperature is given, hot water temperature is given, inlet temperature of cooling water T1 is given, outlet temperature of cooling water T2 is given, condenser is also given, cooling water quantity also given. Calculate the corrected vacuum to standard barometer. You have to find vacuum efficiency, find out the condensate, undercooling of condensate, condense efficiency, and one more thing added in this numerical, quantity of steam entering the condenser. That is how much amount of steam in entering the condenser you have to determine. And then another one, mass of air present in the meter cube of condenser vacuum per kg of uncondensed steam. That is the mass of air you have to find out. The first of all, you have to find out the corrected vacuum. Corrected vacuum means 76 minus HB minus HB. You will get 75.5 centimeter of Hg. Then you have to define the absolute pressure of steam corresponding to the condenser temperature. From this condenser temperature, you have to find out the pressure for steam table. We are getting 0.05622 bar. Again, you have to consider the Cm of Hg, that will divide by conversion factor 0.01332. We'll get condenser pressure of steam equal to 4.22 centimeter of Hg. Then find out N vacuum. That is the condenser efficiency. Again, the same formula. Actual vacuum recorded by gas divided by ideal vacuum. Therefore, 71 minus 76.5 minus 4.22 will get 0.9823. Will get multiplied by 100. Will get 98.23%. You are getting the vacuum efficiency. After that, you have to find the undercooling of condensate. That means condenser temperature minus hot field temperature. That is 35 degrees Celsius minus 20 degrees Celsius. Will get the 7 degrees Celsius. Then find out the absolute condenser pressure, equal to barometer reading minus vacuum reading. Then 76.5 minus 71 will get the 5.5 centimeter of Hg. Again, this same of Hg converted into the bar. That means multiply by conversion factor 5.5 into 0.013322 equal to 0.07333 bar. And this we are already getting the pressure. Saturation temperature corresponding to 0.05999 bar will get the temperature 39.11 degrees Celsius. We are getting the steam table. That is, from this pressure bar pressure, we are to getting the value of temperature 39.11. Then you have to find condenser efficiency. Maximum temperature to which the condenser water can be raised 35.85 degrees Celsius. Therefore, apply the formula N condenser efficiency T2 minus T1 upon Ts minus T1. Put the values 25.6 minus 8.5 divided by 39.11 minus 8.5. Will get 0.5586 into multiplied by 100. Will get the 55.86. There is a condenser efficiency you are getting in this case 55.86. Then last parameter to be determined, last two parameter, the heat lost by steam and heat gained by the water. That means when the steam is passing to the different section of the cycle, that means the condenser section, what happens, the heat lost by the steam and heat gained by the water, neglecting the heat received by the air. Okay, that means in this case only the heat gained by the water. Then you have to apply the formula EMS H1 plus X1 HFG1 minus SC equal to MW CPW T2 minus T1. SC is HF of yellow condensate 20 degrees Celsius and 1900 into in bracket 166.89 plus X1 into 2407.21 minus 117.3 will get equal to 59,500 into 4.2 in bracket 25.6 minus 8.5 bracket complete will get the X1 dryness fraction 0.914. That means CPW is given in this case 4.2 kJ per kg Kelvin. Then you have to apply the Dalton's law of pressure. In this equation, you have to find the pressure of air Pt minus Ps equal to 0.07333 minus 0.05622 will get the pressure of air 0.01711 bar. And the last one, to determine the mass of air per meter cube of condenser at 0.01711 bar pressure and at a 35 degrees Celsius, applying again ideal gas equation. This is the perfect gas equation, PV equal to MRT. put the values, and we are getting the value of m equal to 0.0196936 kg per meter cube. That means you are getting the mass of air, and the volume of 1 kg mass of uncondensed steam is given by Vs, which is specific volume of saturated steam at 35 degrees Celsius. So volume of 1 kg of uncondensed steam 25.25 meter cube per kg. We are getting the values from the steam table. We are getting the value of 35 degrees Celsius. Go to the steam table. Go to the 35 degrees Celsius temperature from line, and you are to getting the value of this one from steam table. The mass of air in 1 kg of uncondensed steam is calculated by applying the gas equation. Again, you have to apply PV equal to MRT. Put the equations, and you are getting the value M equal to 0.489 kg. That is, in this equation, in this given numerical, we have determined the different parameters, and the new equations to be considered in this equation: heat lost by the steam and heat gained by the water. And this is the end of the today's session.